Hello, my name is Sarah Laura Primicheru, and today I'm going to do a video based on this whole checklist, write up code on MATLAB. So to start off, I've done already a recording saying my name, and in order to put that up into MATLAB, so I have the recording put as sarah.wav.wav. So to begin writing up the code, I'm just going to start off with clear all, and then after I'm just going to start to write code for reading in the file. Okay, close bracket, and then equals to audio read, and then just name the file sarah.wav.wav. Okay, and then I'm just going to semicolon that bit there. So that seemed to be a success. And then just to make sure that we can hear, and there is a audio file there with it saying my name, I'm just going to put in sound IP and then FS, and I'm just going to close that bracket with a semicolon, so you should be able to hear it now. So that's it there. You should be able to hear, you should have been able to hear it there. So just as I looked at it there, my IP is put as a double column, so I need to convert it to single. And the way to do that would be if I put in IP equals to IP, and then we put the bracket in, colon, and then here to 1, and then semicolon. That should be it there. So now going back to our checklist, I've done this part. So I've recorded the video and stored it into MATLAB, and then I have this store the sampling frequency used to record the audio signal into a variable fs, which has been done also. Now I need to plot the speech signal in the time domain against time in seconds, and I need to label the axis. So the way to do that would be creating a time vector. So that would be t equals to squared 0 to length of IP, and then we just minus 1 and there, and then divided by fs, and we semicolon that one. So that's our time vector there. And then in order to be able to see it, we need to plot t IP there, and we need to label the axis, so we'll put in vectors must be the same length. What have I done there? Oh, I realized. So I just didn't put the right semicolon. So it's t equals to this here 0 semicolon length IP, close it, minus 1, and then divide by fs. That should be fine there, I hope. So yeah, that is, and then plot t and IP yeah, so I can see the figure down here, so popping up. So that's the speech, that's the audio signal. So just to make sure that I meet the requirements, I'm just gonna label my axis using Y label and X label. So Y label will be the amplitude, there. Okay, so amplitude, and then X label will be the time in, I'm just gonna put seconds. Okay, and then we'll just close everything up, and that should be fine. So if we look at the figure, that's the signal there with amplitude and time labeled in seconds. So with that, it's covered there. So I've covered this part here, labeling the axis. So moving on, then we need to run the following code in MATLAB using this part of code, and then note the values of the variables fs, tone frequency, and noise cutoff. So I'm going to just hopefully be able to copy paste this. Yep. So copy and put that into MATLAB. So that's it there. And I'm just gonna semicolon that one. Okay. So that's this part covered, and just to be able to show you here, the noise cutoff is 18,152, and we have the tone frequency, which is 2541. So looking back there, so at the checklist, so in order to synthesize high frequency noise and a tone, and to add these to the speech signal as described in the example video. So what I am going to do is go back into MATLAB, and as I've said before, so as we have the noise and the tone, every variable is going to be different to other people. So in my case, they're these numbers, so I'm going to use them in the following code. So what I'm going to do is create the noise, and I'm going to call it NS, and that's going to be equal to rand. So the reason why we use rand n is we're trying to use a random signal to be the same size as the IP signal that we created. So rand n here, and then we're just gonna size IP, and then just close it all, and we're just gonna do this here. So that's how we created the noise, and then we're gonna bypass filter it at high frequencies. So BA, or I need to put this in brackets, so BA here equals to, so we're going to use butter, and then 6 as it's the 6th order, and then we're going to use the noise cutoff here, so that's going to be 18152 there, and then we're going to divide that by bracket fs over 2. Okay, and that should normalize it, and we're just going to use it at for high frequencies. So high, oop, and then just close it all, and we're going to semicolon that. Okay, so that's my bypass filter part. And then after, we're going to do ns equals to filter. So we're going to use the filter part, and we're going to put in BANS, close the brackets, so and semicolon, so that will store back into the variable of ns. So that's the noise created, and next we're going to do the tone. So tone will be equal to 0.1 multiplied by cos of 2 times pi times so if we look back at our tone frequency, it's 2541 multiplied by t and semicolon that. So that's tone created there, that part of code. And then we're just gonna put this in this formula here. So IP plus NS and plus tone here, and then we're just going to semicolon that. Okay, just to have a better look at this, so these are all our variables here. So tone, I'm using this little apostrophe up here because it's a row vector instead of a column vector, so that will help it. So that's it there. To synthesize high frequency noise and a tone and add these speech signals as described in the example video. So this is this part done. So next part will be design a second order filter using MATLAB butter function with a cutoff frequency set equal to half the noise cutoff frequency. Okay, so just going back, so we're just gonna continue on, and we're just gonna use the butter function again. So in order to do that, we need to do it BA equals to butter, which is the butter function. This time it's gonna be second order, which we're gonna put in the value 2 instead. 2, and use the noise cutoff, which was 18152. Okay, and we're going to divide that by 2 and divide that by fs divided by 2 here. So that will be our second order low pass filter as required here. Design a second order filter using MATLAB butter function with a cutoff frequency set equal to the half noise cutoff frequency here. So I've done that in that bit of code there. So yeah. Okay. So moving on. So looking back, so in the first video, because there's a certain time limit on me creating the videos, which is just 15 minutes, I have to do 2 videos. So just looking back in the first video, I've covered only this much of the highlighted bits, and now following up, this is the second part here. So draw a signal flow diagram and write out the difference equation and note the B&A coefficients of the system designed. So to be able to do that, we have to go back to the code, and I just have to put B equals to B yeah, just there, B, yeah, that's the B&A coefficient, so this A there. Okay, so as you can see, we have these numbers here as B, so I'm just gonna copy this down here, and we have also A, which is here. So just to be able to draw the signal flow diagram, I'm just gonna do this right here. So okay, so to be able to draw the signal flow diagram, we always start with x and squared bracket n there, and in this case we're gonna have 2 delays. So just to go down here, we're gonna have the first delay. I'm just gonna put this as D, and we're gonna have another one, another D there. So then after, for this case, our y of n is going to be here. So y of n there, and for this to happen, it's going to be added here, and we're just going to put this here. Now the y is going to have another two delays here, so, and I'm going to name them in a second. Okay, and one last bit, we're gonna do the multiplication signs of this case. Okay, so looking at the arrows, we're gonna draw them this way, here, here, and then also 2 other multiplication signs. This drawing is a bit dodgy, so but you get the idea anyway. Here, and this one's gonna be up here as well. So going back up to to be able to determine what our numbers are gonna be, so I'm gonna put here so this first part we're gonna multiply by 0.1892, and just 92, and then after this one's gonna be 0.3784. Okay, and then going down, this last part is 0.1892, so 0.1892. Okay, and then to also do the y ones, in this case we'll have to change the signs. So I'm just gonna change the color of this, and I'm just gonna say it's gonna be -1 in this case. Let's make this a little bit neater here. -1, and this one's gonna be 0.4511, and the last bit is gonna be here -0.2078. So -0.2078 there. Okay, so that's it there. Those are our numbers. So next we have to be able to write the equation. So in order to be able to do that, I'm going to do this in blue. Okay, and next it's going to be just looking at our numbers up here. So I'm just gonna copy paste these again so I can have a look at them properly again when I write the equation down. Okay, there. So this is going to be minus, we're going to convert this to a plus, and this will be a minus in our case now. So when we write the equation down, it's going to be y squared bracket of n, and in this case it's going to be equal to this one here. So it's 0.1892 multiplied by I'm just going to write this, multiplied by x of n, x of n, and then we have plus our other variable, which is 0.3784, and then it's going to be multiplied by x squared bracket n minus 1, and then also plus the last coefficient of b, which is going to be 0.1892, and it's going to be multiplied by x of n minus 2, and then moving on to the y parts, and we have plus or minus 1.0, or also 1, multiplied by y squared bracket of n minus 1, and then minus oh sorry, this is not 1 is here, so this is going to be 0. Got this wrong. So this is going to be plus 0.4511, and this one here is going to be minus 0.2078, and we're going to multiply that by y n minus 2. Okay, so that's the equation there, it done, of the signal flow diagram. So just looking back at it. So that's what happens there. Those are my B parts, that's my Y. As you can see, I changed the signs compared to what MATLAB has given me, and from there I use that to convert it into an equation. So if we go back up here, I've drawn the signal flow diagram, I wrote the difference equations, and I noted what the B and A coefficients of the system are designed. So if I go back here, I can highlight this, and then next it says calculate by hand the first three outputs of the system if the combined signal, speech, tone, noise is applied. So in order to be able to do that, I'm going to take this here, copy, and what I'm going to do is, so I'm just going to go back. Sorry, unfortunately everything deleted, so I had to just redo everything again quickly. And where we left off, where it was the B and A coefficients in MATLAB, and then I showed how I did the signal flow diagram and how I got the difference equations. And then just quickly, just to move on to this last bit here, calculate by hand the first three outputs of the system if this combined signal, speech, tone, noise is applied. So the best way to do that is if I type down here sig squared bracket 1, 2, 3, this will give me the first three outputs of the signal, or the first three inputs, sorry, of the signal. Why is that not? Why? That should be able to work. Let me have a look. Just there. Where is it? Sig. Let me try this way. 1, 2, 3. That should have worked. No. I've just been putting the wrong bracket in, so that'd be sig. So we maintain the curly brackets 1, 2, 3 to give the first three inputs, and just not put the semicolon in. Yeah, and those are our three inputs. So I'm gonna copy all this there, and what I'm gonna use that in the following calculation to fix that last part. So ants of inputs, just to remind myself what this is, there. Okay. Yeah, so in order to get the right calculations, I'm gonna begin with the first part, which is working out y0. So y squared, so y square of 0 is equal to, so using what we have here, so this is going to be, just to note this is going to be, x0, this is x1, and this is x2. Okay. Continuing on to our calculations, so what we're gonna do is find whatever the parts y0s are. So just delete this dot here. Yeah, and then I'm just gonna be typing our calculation, and we're going to make it so looking back, so we had this number here, and then we're going to make that multiplied by x0. So in this case, x0 is going to be this number, so this number here. And then what's going to happen is then we're going to add, and we're going to add so this is gonna be 0 and minus 1, so this is not valid. To continue on, this one's not valid, or give me 2 seconds. So x of 0, this is going to be x of 0 again, so this is going to be here. We're just going to change this up, so 1 minus 1 is oh no, this we have 0, I'm sorry, so this is going to be off the books. And then we have y 0 minus 1, that's not good, and then this one's not good either, so we're just going to be left with this part of the equation here. So then moving on to y bracket 1, and that's going to be so we're going to have this number again, so I'm just going to look back up here. So y, so 0.1892 multiplied by, in this case it's going to be x1, so x1 is this number here, so okay, this number here, and then it's going to be added to plus here. So if we have 1 minus 1 is 0, so we're going to have this number multiplied by x of 0. Oh, 0 multiplied 0.3784 multiplied by x0, so x0 in our case is going to be this number here, and this number here. I'm just going to separate these to make it more visible. Okay, and then also that's there. Then moving on, we have 1 minus 2 is going to give us minus 1, so that's going to be 0, so it's 0 multiplied by this still gives you 0. And then next we have this part here and this part here. So with those parts, then all we're going to do is just going to add in this case, and it's going to be this multiplied by y0. So y0 will be whatever comes out of this. So if we want to put this into MATLAB, just to calculate this part here, that's going to be into this. So we have this part here, and that's going to be 0.019. 0.019, and we'll just put that equal to this. So y0 in our case is going to be that again. Okay, y0, and then after the last bit we're missing is, let's see if this is incorporated as well. So we're trying to incorporate y1, so y1 1 minus 2 is going to give you minus 1, which is not available in this case because 0 times this number still gives you 0. So if we instead of brackets, because MATLAB doesn't really work with brackets, we just put this bit in, and that's going to be here. Our answer is going to be about that much, so I'm just going to put in this. So that's going to be our y1 output, and then after we're trying to find y2, and that's going to be so equal to, sorry, so that's going to be equal to this by x of 2 by this number, because that's x2. Okay, and then we have plus 7 plus then this, if we put in 2 minus 1 is 1, so that's going to be x1 there, multiplied by x1 in our case is this number here. Okay, and then we add that to 2 minus 2 is 0, so x0 is going to be plus this number by x is 0 there. Okay, and then y, so n which is going to be 2 minus 1 is 1, so whatever y1 was, so this number, so it's going to be added to this by this multiplied by, and I'm just going to put the multiply sign as well here, so multiplied by y1, so y1 in our case was this. Yeah, and then here we have 2 minus 2 is y0, so it's going to be 0, so it's y0, so it's that number multiplied by y0, and just let's not forget the minus. Yeah, minus y0, which was this number in that case. Okay, so if we copy paste this part, copy, and we put that into MATLAB to calculate our last part. There's something wrong with this expression. Valid text number, which one is it? Plus. Oh. Minus. I'm just gonna separate these just in case. Okay, that should be alright. Yeah, so that's it there. So those are my values. I'm just gonna copy paste this as well, just so we have a record of all these values down. Okay. Okay, so those are the calculations of all the outputs using the inputs that we have of the signal. So So moving on to this part here. So we've done this, calculate by hand the three outputs. So I'm just going to highlight that part here. So now, in order to verify whether our outputs are correct, we need to filter out the combined signal using the MATLAB filter function. So that's what we're going to do, and then compare it to our hand calculations. So going back into MATLAB, what's going to happen is we will use the filter function. So with this here and B, and then A, and then we're going to use the signal sig 1 to 3. Okay, and then we should be able to get again, there's something wrong here. So filter, did you mean, oh yeah, I missed one bracket, so copy. Oh yeah, and I wasn't supposed to put the semicolon in. Yeah. There you go. So these are our answers. So if I compare to the calculations I've got down here, so y0 is this number, which is very accurate. Y1 is a little bit more off, but and same as y2, but they are close enough, so that should be correct. Okay, so that's that. Next, I'm just going to add another couple of pieces. So y equals to filter B, and then A sig okay, and then it's going to be y 1 to 3, 1 to 3, yeah, so those are still our values, and then we're going to do a format short, and then do this line again. Yeah, so I didn't have to do that, but that's just another way in case I got too much of a long number or anything of that sort. But I just showed it just in case it had to be showed. So that's done there, part of the list. In order to filter out the combined signal, I verified also the calculations. So moving on, will be design a minimum order filter which will reduce a high frequency noise by at least 60 dB with a maximum of 3 dB ripple allowed in the passband. The passband is 0 Hz to fs 4 Hz. So in order to do that part, I'm just gonna quickly, because I'm running out of time, it's gonna be N to W here, and we're gonna use the but ord, and then it's going to, we're gonna do 0.5, and we're going to change that number to whatever our noise cutoff is. So in that case, it's going to be 18152, 152, and then we're going to divide that by, in bracket, fs divided by 2 there, and not to forget about the 3 dB and the 60 dB. 60 dB, and we have to semicolon this. Invalid expression. There's something wrong with my expression here. Oh, I forgot to put the equal sign. So I'm just gonna. So just to fix that part there, I'm just gonna copy paste it here. And yeah, and that should be able to work. There, yeah. So that worked there. So we're gonna find out the values of n, which is 8, and the values of w. Do you mean double? Yeah, sorry. Okay. So those are my values, and then what I'm gonna do is I'm gonna be a equals to, I'm gonna use the butter function, and then we're gonna just specify the n and w and semicolon that. Okay, so that's that part done, as far as I know. So this part, so we've designed the filter, and then we have to move on to creating a second filter using MATLAB functions to reduce the tone to 40 dB. So I'll be doing that and continuing on. So yeah. So moving on, I'm gonna specify here so B1 and A1 equals to butter of 10. Okay. So we have 10, and then after we need to use the tone. So tone and frequency is 2541. 2541 minus, I'd say we go back around 50, and then we do the same, but we add 50. So I'm just gonna do this and add a plus here. Yeah, and then split this, and it's gonna be f, just use the bracket, f s 2. Okay, and then this is for the stop. So we're gonna use the stop command here. So just stop for the stop band. Okay, and then after semicolon this. So to continue on, and then we're gonna use z-plane. Z-plane. Z-plane of B1, A1. Okay, and then after we're just gonna do what we did to the top as well. So we're just gonna use the butter function again, but in this case it's going to be this. So it's gonna be B1 A1 butter, and then we're going to butter, instead of 10 we're gonna do 4. So copy, I'm just gonna use the same thing over. So butter, oh yeah, so there, and you stop. So that should be fine, and then we have the z-plane A1 and B1 again. Okay, so to continue on, we have to put in whatever z-plane of B1 and A1. Okay, and then after we are going to do 2541 divided by brackets of fs over 2 there. Okay, so this number here, we just want to check that the frequency is attenuated by at least 40 dB. So in order to do that, we want to do frequency, so freq-z, and then B1 A1 here, and using this graph here, we should be able to check the attenuation. So just using zoom in here, we just want to see how much it is attenuated by, and it should be at least 40 dB. So as you can see here, it is. Okay, so what I'm gonna do here for this last bit, I'm just going to do freq-z B1 A1 and then 10,000. So the reason I did this is because in this case here the frequency response is a bit jagged. So when I do it by 10,000 here, that will make it just a bit, the filter more smoothly. So as hopefully that worked there. So I'm just gonna go down here and I'm just gonna put this here. So yeah. Okay. Okay, so that's that part there. For some reason it's giving me errors. Not sure exactly what it is. But to move on, so I've done this part here. I've done this part here. So just following the last two parts, apply both filters to the combined signal. The output of one filter is to be the input of the other one. Plot the magnitude frequency content of the input and output in hertz and label the axis. So in order to do that, I'm just going to quickly do y equals to filter, and then b a sig, and then we're just going to semicolon that, and then after it's going to be y1 equals to filter of b1 a1 and y. Okay. Y of y, and then semicolon that. And then after we're gonna just do the axis, so fax equals to I'm just gonna do this to here, and that's gonna be 0 to length, spelling this wrong, length of IP minus 1, close the bracket, and then length of IP and then multiply by fs. Multiply by fs. Oh, I forgot to put in the brackets. Just close it there. And that should have been able to work now. And here is supposed to divide it, so hopefully that works now. Did you mean yeah, so that worked there. And then we're just gonna plot it. So plot facts. Yeah, facts. We're gonna plot facts, the absolute value of FFT and Y1. FFT of Y. Oh, sorry, no, FFT of sig. Yeah, there, and then after we are going to hold on, and then do plot again. So just to show you what I have so far, so this is the signal here, and so just to show you what I have here so far, so this is the signal itself, and then just to show you how the signal is attenuated and it won't have any high frequencies. What I'll have to do is after the hold on is plot this whole thing again, and copy, paste, and then we're gonna do facts AB as FFT, and instead of sig it's gonna be Y1. Okay, so just to show you what's going on here. So that's our speech signal there, and the signal is attenuated, and the yellow, so this yellow up here won't have any high frequencies in this case here. So as you can see that there, and then the full thing here, just to show you. Yeah, so that's it there. Okay. So just to not forget the last bits, just Y label and next label. So Y label, that's going to be the magnitude there, and then the X label is going to be frequency in hertz, HZ. And just to close that, we have there semicolon, so you can see that the labels are put up there and the graph is showing there in that case. Then just to show, so I've done this part, and in the final video I'm going to show you how to do this last part here. which is identify a low frequency component that will produce a significant phase shift in the first filter, and pass the sinusoid of that frequency through the filter. And then I'll verify that the phase of the tone has been altered by the expected amount. So moving on to this last bit here in this part of the video, so we're just going to do close all, and then after we're going to do a frequency of Z, and then B comma A. Oh, sorry, B comma A. Okay. So this is a plot of a low frequency sinusoid, which looks better. High frequency sinusoids look jagged, as they only have a few samples per cycle. So then I'm going to show you the phase. So the phase, I'm going to show you the phase shift. So I might look here at a phase shift of around 45 degrees. So if I just zoom in here, so if I just move this here, so that's it there, around minus 45 for some reason. I don't think it'll go down. So yeah, that's it there. And just to do the last bit, so I'm just gonna do 0.12 multiplied by Fs divided by 2, which gives me an answer here. And then what I'm gonna use tone equals to cost of 2 multiplied by pi multiplied by so just using this number 2880 multiplied by t, and then closing the equation off, and then going on, what I'm going to do is y equal to another filter function, filter b comma a comma, we're going to involve tone in this case here, okay, and then again we're going to do close all, and then plot tone, close it there. Yeah, so plot tone, and then we're gonna hold on again, hold on, and then we're gonna plot y, okay. So then just looking at our graph down here, I'm just gonna have to right click onto it. If it works. So I'm gonna put it on the horizontal view, and zoom. For some reason it's not working. So I would have put it on horizontal view, that's what I'm looking for, and then I'd get the phase shift of about 48 or 45 degrees when I zoom in. Now if that works for me, I'd do that there. So I'm just gonna do okay, so yeah, I managed to zoom in now there. So the more I zoom in and I look into it, so yeah, that looks like about 45 degrees when it's zoomed in. So that would be the face, and that's the last requirement done. So we were asked to identify the low frequency components that will produce a significant phase shift in the first filter, which I have at least pi4 radians, and pass the sinusoid of that frequency through the filter. And then I had to verify that the phase of the tone has been altered by the expected amount. So that's our expected amount there, and that's it. So just to highlight that last bit, and then this final complete the checklist and verbally explain each element of the checklist. So that's all been done. So hope you liked this video, and thank you for watching.